Hello everyone, my name is Nirich and I work as an engineer at AI Crowd. Today I will be walking you through the self-checkout puzzle. So what's a self-checkout puzzle about? Essentially we have videos of different items going down a conveyor belt and our job is to identify the unique items and their counts and therefore calculate the total bill amount. Total bill amount will be used to grade your submission and therefore rank you on the leaderboards. But it is important to note that this application just serves to explain interesting topics and techniques in machine learning, and the techniques that you learn through this puzzle can be applied in many places. So, what are we looking to help you get out of this puzzle? Firstly, we have two notebooks, and the first notebook more or less serves to help yourself get familiar with the data set, the problem itself, and how you can use naive approaches first or more computationally expensive approaches to try and solve the problem. We'll be going through the notebook in detail, and in the second notebook, you'll be using pretty advanced techniques like using object detection and deep sort for object tracking to track unique objects in a video to accurately determine how many objects are there and their classes, and therefore the total bill amount.
Now I'll begin walking you through the first baseline. So the main purpose of this notebook is to help you get acquainted with the dataset and the submission formats, and also introduce some naive techniques to try and solve the problem. A full disclaimer though, this approach is not going to be that great at actually trying to solve the problem, but you'll be learning a thing or two which can be useful in many different applications. And it will help you think a little bit outside the box when you encounter a similar problem. So what we'll be learning in this notebook is A, trying to perform image stitching to stitch different frames of a video together, or to any images for that matter, and B, trying to use HSV ranges to actually detect the class or the type of fruit in this case, or detected region. And consequently, we'll be calculating the total bill amount, and you'll be surprised to know that the results are pretty decent for such a naive approach, but obviously using a deep learning based method can yield better results, as we'll see in the advanced notebook down later. So the first thing we do is download the Aircraft CLI, which will help us authenticate ourselves and also will help download the dataset for the building self-checkout challenge, and also make submissions directly from the notebook. And we will be unzipping them to the data directory and also installing the latest version of OpenCV. So once we've imported the libraries that we need, we will start unpacking and taking a look at the dataset. So the annotation files that go along with the dataset have a format that looks like this. We have keys for every video there is, so each one of these IDs. The video IDs are essentially just the names of the video files without the .mp4 extension, and each one contains an object with two keys in it. First key is the bill value, which is float, which represents the total bill amount, and also the annotations, which is a list of 40 objects. And I say 40 because there are 40 frames in each of the videos. And each object consists of a variable number of keys. Each key represents a unique fruit in the video. So as the video goes, as the items go down the conveyor belt, their positions change across different frames. However, the ID remains consistent across different frames. That's the reason we use a unique ID for a particular unique fruit. And each one of those ID objects contain within them a class, which is a string, which returns the type of actual item it is, and the bounding box, which returns the min, the x min, the y min, and the width and the height of the bounding box with respect to the top left corner. And throughout the notebook, you'll see many sections where the code has been hidden. This is to make it a little less intimidating to new people who are new to machine learning and Python and coding in general. And so in case you are curious at any point in time what's going on within the cells, feel free to press show code, which will bring up the code within the cell. And if you would like to close it again, just double click on this empty area here and it'll collapse. So in this case, we will be using some utility functions to convert the JSON files to data frames that are a little bit easier to work with in code. And another thing that this cell does is extracts the frames out of a video and saves them in a particular directory. Performing both these steps together results in a data set that we can start working with. So what the data frame looks like is contains video IDs and it contains frame IDs for in the video, so 0 to 39 for every video. And each frame, since the frame has been extracted out of the video and saved to a path, it now has the file path to that frame. Then it contains the list of bounding boxes present in that frame and also the classes for each bounding boxes in the same order. The final column is just a bill value for the entire video itself, so it's going to be the same for all the frames. Taking a look at a single video, a single sample, what it looks like is essentially 40 frames in which the fruits go down the conveyor belt, and for each frame we have the bounding boxes and their respective classes given by the class. class key. And in this case, we are visualizing the frames 0, 9, 18, and 27. Coming to the first interesting part of the notebook, we'll be taking a look at a technique called image stitching. So, like I explained in simple terms earlier, image stitching is a technique where different images are superimposed on top of each other on similar key points or similar features. So, it's not the same as concatenating images where you're just keeping them next to each other. Instead, you're trying to identify the unique features in both the images. And if needed, you would also perform warping the perspective of one image with respect to the other and then blend them together on the common features to result in one long continuous image. So in this case, if you have two images of the scenario, let's say, and combining them together would result in something that looks like this. Note how there is a difference in perspective in both images. One is parallel, and one in which the desk is parallel, and the other in which the desk is slightly skewed, which essentially tells us that it's in a slightly different perspective. However, the technique can figure that out and kind of warp the perspective of the other image to match another one and blend them together seamlessly. So the code which actually performs the image stitching is contained within this cell. It is abstracted, but in case you'd like to take a look at it, feel free to take a look at it. So we won't be diving too deep into what the code does, but in short terms, all it does is detect feature points in each image. And then another method tries to go through all the feature points and try to find the common ones. And it takes in two images and performs this operation on them. We've copied this class over from this amazing repository because of its ease of use. However, we copied it over because we are overriding and making some minor changes. Specifically, in this case, it will be the smoothing window size. In this case, it's 200. This window essentially corresponds to the region where the blending will occur and the detection for features. So taking a look at this operation performed on a single video. Before that, it's important to note that we really don't need to merge all the 40 frames of video together because the information contained in many of them would be very similar to one another, so resulting in quite a lot of waste of computation. So in this case, we will be taking images at certain discrete intervals, in this case, interval of 9. And so we will be taking the images frames 0, 9, 18, 27, and 36 and merging them together to one long continuous image on top of which we can perform object detection or any other simpler operation as well. So performing this operation for one video results in something that looks like this, where you can definitely see some blurriness and some artifacts going on, but for the most part, it's good enough for us to start performing object detection or any other, HSV thresholding detection or any operation for that matter. It's good enough to start performing that. Now we will write a utility function which, given a video ID, it performs this operation for that video and saves it as one processed image. And we will be using the same frame gap of 9 for all videos. Then the only thing left to do is perform this step for all the samples in the validation dataset. And we are doing this, though you could directly just do this for the test set. We are doing this for the validation set just to get an idea of, in the next steps, we will be analyzing the color ranges for different fruits and stuff. So in the future, it will be good to validate it against some classes we know, some results and some labels that we have, which is why we're doing it over here. Although you could proceed to just do the same operation on the test set with a little bit of the next thing we'll be looking at is performing object detection using simple HSV filters or HSV thresholds. So what's HSV? It essentially stands for hue, saturation, and value, using which we can represent any color in a given pixel. And the idea behind it is that you have an upper threshold and a lower threshold, and any pixel or region of pixels which fit within the threshold is detected as a particular contour or region. We have multiple patches of these regions, and we then take the bounding box or the minimum and the maximum extents for these regions as our bounding boxes. And the goal here would be to analyze the images so that we can come up with clever ranges for each class of items so that when you apply a filter over an item, you get the contours for a particular class of items, say a fruit type apple. So you get all the contours detecting all the apples in the image, and then you can take the bounding box off them. So what that would look like with random ranges in this case. So in this case, we have random color ranges. It would just detect random patches of color given a particular range, which is present in this code, and it would then draw the contours around it. Then we will need to do the slightly tedious task of analyzing the images to come up with clever HSV values. So this is where you are encouraged to perform your own kind of exploration and figure out what color ranges work best and give you the best scores. And we can make a few assumptions from looking at the dataset visually. We know that apples are contained within the red and sometimes even the yellow color space. The mango is predominantly red and yellow almost all the time. The orange is in the orange color space. The lemon is in yellow. And the onions are in a blue, like a purplish, reddish, pink in that region. Visualizing it using a three-dimensional graph results in something like this. This is the visualization for a single image, and it would be a good idea to take the average of multiple images. What it looks like is we have different patches of ranges of color, and we can kind of go about determining what class we want to associate this region with. For example, this region could be regarded as lemons, and we would take the uh, values represented, or I mean, values corresponding to that region for threshold for the lemons and experiment. It's more of a trial and error, but with a decent bit of analysis, you should get good ranges which work for almost any image. This is where the performance of this method can degrade quite a bit because it's impossible to find a threshold range that works well under all kinds of lighting conditions because the lighting conditions can sometimes be really varied. But you can try to prune out different classes, colors, and perform other kind of post-processing techniques to improve your score. We'll be taking a look at a couple of examples, but you are highly encouraged to perform your own kind of uh, experiment with it a little bit and come up with your own solutions. In this case, what we'll be doing is writing a utility function that can detect a particular type of object, given the name of the object and the path to the image. And for each object, we have defined the color ranges after doing a little bit of analysis on our end. This is where you're encouraged to do your own analysis and come up with or change the ranges that we've selected to ranges that might give you a better score. Most of the difference in scores can come from just simply varying values. What it returns is the contours, and the contours we saw were just polygons connecting the region, and we will be taking the bounding boxes, the minimum and the maximum coordinate along each axis. So performing that step results in an image that looks like this. So notice here how we've given the path to the image and we are trying to detect lemons, and it's detected lemons perfectly, but other things which were close to the region that we defined, at least the region within the threshold that we defined, were also detected, which are not lemons. So you will need to prune those out and clean up, and you can use any technique to prune them. Here we'll simply be checking for the region of those areas and trying to see if they're less than a particular uh, value. And this value has also been determined by analyzing a few samples from the dataset. And you could use other clever techniques as well to prune out false positives essentially. And performing this step iteratively for all the different classes would result in an image that looks more or less like this, where each class has been detected pretty well. They will have to be accurately labeled. So it's pretty good considering that it does not utilize any machine learning or any advanced technique and just uses ranges of colors to determine different boxes. So this function, utility function, would try to perform this detection for all the different keys, all the different types of fruits present in the dataset. Another thing that I mentioned earlier is the fact that you are not given the price of each class of item in the dataset. It's up to you to figure out what the price of each item is. In case you're looking for the solution for that, this is where you'll find it. So it's you're coming back to what it is. It's essentially middle school math where we have a linear equation of five unknowns, and we are essentially trying to solve it. So you need five linear equations, and we have quite a lot of samples in the validation set where we have all the values associated with them. So we have everything that we need. Now it's just a matter of using them accurately using NP numpy's and linarg.solve function. It's pretty simple to solve such equations. So that's how you can do it. There are alternative ways to do it as well, but feel free to try what works best for you. And in this case, solving the equation in this cell would be the solution to our problem. And if you would like to take a look at it, go ahead. And what it would result in is the price of each class. We will then be making use of that in combination with the classes that we detected using the threshold values to calculate the total bill amounts, which should be used to grade our submission. Now, putting it all together, we need to perform the same pre-processing to the test set as well, because then we will need to detect the various items on the test images, which have been post-processed. But one thing to note is because we are stitching them together to form a single continuous image, the object detection score is going to be pretty bad because we are not exactly performing accurate object detection on a particular frame. Instead, we're just merging them together and taking all the frames and just performing detection on top of them just for the classes and to calculate the bill amount. So our object detection score or the secondary score is going to be pretty. Once you've performed the operation for all the files, you should be left with the bill value for that particular cell essentially. Now we'll start creating the submission file itself in a particular format, and you'll quickly notice that the format is very similar to the format that we had for the labels, except a tiny difference is we have the inclusion of this confidence key in each ID's object. And confidence is a key that's usually given by an object detection algorithm when it detects an object, and this is in deep learning where you use YOLO v5 or YOLO or something like that. And in this case, we will not be using any of that. So we will be just filling all these cells with zeros, but it is important to include all these as part of submission, even if you're not actually detecting them. You could just fill them with zeros instead. And the biggest thing that we will be trying to fill for sure, trying to fill accurately, would be the bill value, which is the primary metric, along with the count of classes. This cell would help you generate submission file by performing the detection on top of all videos in the test set. And once you use the utility function to actually calculate the bill values and convert the annotation format to the right format, you could then create a submission directly to Aircraft using the submission create method, which would take in the challenge name as a parameter and also the JSON file, which you're saving as the output as a parameter. Once you submit this, you should be given a link which will directly take you to your submission where you can check it. Following this, we have some additional sections where you can, a bunch of ideas you can explore and try to improve your score even using the simple method. You'll be surprised that this simple method returns a decent primary score, although it's not going to give any score in the secondary score, obviously, because we're not performing actual object detection. But if you wanted to boost the primary score further, feel free to actually play around with the code and figure out different color ranges or different frames to stitch images with, or any techniques that you think would help boost the score. Feel free to do them in this notebook.